So question 10. Question 10 is quite a straightforward question as well. Just one thing to be very careful, the incident angle is not 62. Okay, most common mistake happens when students use the angles here directly. Remember, your angle is always between the light ray and the normal. Okay, so once you know this, use your, because this is from less dense to a denser medium, you can use this formula, n equals to sine over sine r, and you find that your angle of refraction is 18 degrees. So similarly, to find the critical angle, just use the formula, plug in the right value, you find the critical angle. Okay, then after that, you have to explain why, what do you say? Why the light is not, the refracted ray is not as bright. There are actually two explanations. The first one is that some of the light get reflected away. So what I'm saying is that this light go into the water, and of course it's going through refraction. Most of the light is going through refraction, but some light will get reflected out. Okay, I will read portion. Okay, this is one explanation. Another explanation is that some of this light energy is going to be absorbed by the water. Okay, that's why the deeper you dive into the sea, the darker it gets. Okay, because the light energy is going to be absorbed by the water itself. Okay, so the second explanation can be some of the light is being absorbed by the water. Okay, and so the intensity of the light actually weakens. So I have to complete the diagram, so it's very simple. So if this 28 is going to bend towards the normal, so bend towards the normal, indicate direction. When it hits the plane mirror, make sure you follow the law of reflection and bounce off at the same angle. Okay, that will be all. Okay, question 11 is again very straightforward. Be very careful with the scale here, especially this one, 5 milliseconds. So down here, how do you know the peak voltage? Just count here, 1, 2, 3, 4. 4 square multiplied by 2. So you get 8 volts. Calculate the frequency. So this one, first calculate the period of one complete wave. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 multiplied by 5 milliseconds. So you will get 40 milliseconds as your period. F equals to 1 over T. You get your frequency. So down here, you are supposed to trace a new waveform. So everything is the same, but the frequency of the voltage is now half. Okay, so in that case, they also tell you that the horizontal scales is the same, 5 milliseconds. Down here is also 5 milliseconds. So meaning that you will be able to see two waves lah. So 1, 2, 3, 4. So you will be able to see a wave that is going same amplitude. Can? Yeah? Just squeeze two waves into the thing. Okay, this one is actually a giveaway. They try to confuse you with the frequency. Of course, you are not expected to remember infrared is what frequency. You are supposed to deduce the frequency from this table. Okay, so what you need to know is that how do you deduce? So you know there's a visible spectrum. You have infrared and you have ultraviolet. Okay, just outside the visible spectrum. And you know that your infrared is actually in the lower frequency. So on the left, what I'm writing here is your frequency. What you have on the right is your wavelength. Yeah, so they tell you that, okay, my visible spectrum is from 400 nanometer. So towards the violet side, you will have the shorter wavelength. Towards the red color side, you will have the longer wavelength. So since you already know the speed of the wave, you can work out when your wave is 700 nanometer, what is your frequency here. So you know that for your red color, your wavelength is 700 nanometer and your frequency is this. Okay, so you notice that all these values 700 and this thing is not coming from your memory. It's actually coming from the question's context. So use this information, you realize that okay, in order for the wave to be infrared, my frequency must be lower than this value, calculated value. And if you compare this to the frequency table here, you notice that only radiation A would have a lower frequency than this. So therefore, your A is the answer. The use, just take one use from your thing. Question 13 is very straightforward, just because unlike charges we attract. Okay, now question 14, although the circuitry looks quite complicated, is actually your motor. Instead of a permanent magnet, now they expand it and make it into an electromagnet. Okay. Now this electromagnet, this is the electromagnet. Now this thing here, FG, is neither a AC or a DC. It's actually a very specific voltage signal given by this diagram here. So you notice that the voltage actually alternates. Okay, the alternates, and they tell you that F is at a higher potential. So meaning that for your, let's say this part, they are saying that FG will be at a positive voltage, and positive voltage they tell you already, F will always be higher. A positive voltage indicate F is higher than G. So F is higher than G. Okay, in the first minute. Okay, that's what the whole question context is about. Okay, so now let's look at the question. So they ask you what are the poles in the solenoid B and C. Solenoid B and C is this guy here, B, C. So this solenoid is actually connected to another DC battery source, and it goes positive, negative. So use your right hand rule. So let's say this is the core solenoid AB. You see this wire here is wrapping on top. So my finger should go this way and it will go this way. On top, right? Yeah, so that's why my north pole is actually at B. So my B will be having a north pole. Similarly, if you use your right hand grid rule, you will notice that north is here. So meaning that south is here. So when you answer the question, please indicate carefully north is at B and south is at C. Otherwise, you enter the gray area and you may not, I don't know whether the marker will be strict or not. Okay, so B, what will happen to the rotation of the coil? Now they ask you in a very specific manner, the first 2 minutes. So the first 2 minutes is until here. And they, in the question's context, they also tell you this information, 5 rotation in 1 minute. Meaning that for this first minute, there will be 5 rotation, there will be 5 rotation. Okay, so when you're answering questions like this that is very specific with the time duration, you must include as accurately as possible in your answer using the information given in the question. So it's not just the direction of the rotation, you have to indicate how many turns it has rotated. Okay, because they ask you to describe. Okay, so you need to describe as accurately as possible. So now let us look at how does this thing will rotate to which direction. So in the first minute, F is at a higher potential than G because it's positive voltage. F is at a higher potential, so this one is positive. So this guy goes this way and then go into the coil. So use your left hand rule. So this finger is your north to south pole, okay? And now your current, this finger is going up. So rotate, rotate, rotate until the finger go up. And this is your north-south magnetic pole, and you see that your force is actually going down. So meaning that in the first minute, this thing is going down, so naturally this one is going up. So it will go in a anti-clockwise direction for the first half minute. Okay, so let's write down what is going to happen. So in the first minute, the coil is going to rotate in anti-clockwise for 5 complete rotation. Now, when you enter the second minute, the voltage is going to flip to the negative side, meaning that this is no longer positive, this is no longer negative. So this will be negative, positive, and because of that, you see, your magnetic field is going to be constant, just your current is changing. So if you are not convinced, use your left hand rule again. You will realize that now the direction of rotation will flip. So you go clockwise. So just answer here in your second minute, the thing rotate clockwise, 5 complete rotation. You got the full mark. Okay, question 15 is about your Faraday's law. So why the lamp glows, you have to point out that when the magnet start rotating, the coil here is going to experience a change in magnetic field strength, and so by Faraday's law, there will be an induced EMF, and therefore your lamp actually glows. Okay, alteration, there are many alterations. Increased number of coil, stronger magnet, lower resistance wire, a lot of them, rotate faster. Okay, so as long as you state one, you get the answer. Okay, last part. So what happened to the U-shaped soft iron? So first you must be able to identify that it will not glow as bright, and that is because the soft iron actually serves as a concentrator. So the soft iron will concentrate the magnetic flux from the magnet and then direct it through the coil. So without this soft iron, the coil will experience a lower rate of change in the magnetic flux, and hence a lower induced EMF, and hence less bright. Okay, because the flux is no longer concentrated to the coil. Okay, finally section B. This is a database question, pretty straightforward also. So how do you find the time? Because you know the torque speed, you know the distance from, see, torque speed is here, distance to torque is here, so you can find the time. Then after that, you are asked to calculate the energy absorbed. Just use the okay, if you look at this data, for those of you who do not know where to start, the sun's radiation at the Earth's surface is actually given in W per meter square, so it's dependent on the surface area. So because of that, you need to use the data here, the effective surface area exposed to the sun. So you just take this ratio, this rate, multiply by the surface area, you'll be able to get the power received by the iceberg. And then you multiply by the duration that it is on top, you'll be able to find the amount of energy in joules. Estimated the mass that is melting, use your latent heat of fusion, Q equals to mLF. This energy is the energy absorbed. So use the data from the table. This comes from here. Okay, use this data, substitute here, you'll be able to find the mass. Okay, down here state two assumption. Actually there are more than that. Number one, actually when the ice starts melting, the surface area will be changing, but in our calculation we consider the surface area constant. Number two is that actually the ice will absorb energy from the environment, from the water also, but in our calculation we are assuming that the energy is only coming from the sun. Okay, so actually the energy absorbed by the iceberg is not is more than the energy, the value that you calculated. Okay, another thing is that heat loss to the surrounding. So that's another way of saying it. Instead of saying energy absorbed from the surrounding, you're saying energy lost to the surroundings. Energy lost to the surrounding. No. Okay, if you write energy lost to the surrounding, you get 0 mark. Okay, because the ice is at a lower temperature than the surrounding, and so there will be no energy lost to the surrounding. It's always energy absorbed. Okay, so please ignore this. This is wrong. Last one, sun's position. Yeah, so we are assuming that the sun is at a fixed position, so that's why the radiation from the sun is a constant value, but actually it is not, right? When the sun rises, it is gentle, but when it is at noon, it is at the you receive more energy because now it is directly above you. Okay, so the sun's position is changing, and so therefore the power from the sun is actually also changing. Okay, for part E, you just need to compare how much power or how much time is required to melt the entire ice. So I first calculated the energy to melt the entire ice is this much, and then I calculate from the power rating of the station how long will it take to melt the ice. So I realized that although you see the first part, this one 1.42, this 6.8, looks like this one takes longer time, but if you look at the power here, okay, the sun will take a much longer time to melt the ice. So of course, if we are just talking about efficiency and we are not considering whether it is green or not, then obviously the power station will be a better alternative because it takes shorter time to melt the ice. Okay, so just write down here, it is more efficient because it takes a shorter time to melt it. Okay. Last question. Why the man hear two sound from this thing? So you have to excuse me. So you have to point out that the first sound actually comes from the thunder directly to the man, but the second sound is actually the sound coming from the mountain, okay, when the first sound is being echoed from it. Okay. Why it is softer? That is because the mountain surface is irregular, meaning that it is going to be a dispersed reflection. So because of that effect, the sound will appear softer. You can also explain it in a different way. You can say that the sound energy is actually being absorbed by the mountain's surface, or is being absorbed by the vegetation on the mountain as well. So I will accept both answers. Okay, for part 3, it's easier if you draw a diagram. So what happened is that this is where you are standing. This is where the thunder actually strikes, and this is the mountain. So the first sound will come from the thunder to you with a distance of x. The second sound need to travel from the thunder to the mountain, and from the mountain back to you. Okay, so this time lapse is actually the time difference between the second sound that you hear, which is the echo, minus off the first sound that you hear. So if I use the time, if I want to find the time, it's actually the distance divided by the speed of sound. So the distance here is actually 2.5 minus x plus 2.5. So I will get 5 km minus x. So because this speed 340 is actually meter per second, I have to convert this kilometer into meter. So 5 km will become 5,000 meter. So similarly, I do the same thing here. I minus off, do the algebra, you will get the distance x. Okay, x is this, right? So that's the distance you are looking for. Amount of charge, use this formula. These two value actually comes from the question. So go and look for it, you will find it. Then after that, use P equals to VI again. These are the value from the question. You will be able to find this. Down here again, you are using just a different power formula. All this thing is either from your part 2, if not from both of this is actually coming from your previous calculations. I think the time is from the question's context. Okay, last question, draw the circuit. This one is very straightforward. Just draw a series circuit, ammeter connected in. Okay, I'm going to draw for you lah. So draw the battery. You have this resistance of this coil of wire. So draw the coil of wire. Okay, your ammeter is going to be in series. Your voltmeter is going to be in parallel. So draw the thing. Do you have a switch? No, we don't have a switch, but usually there will be a switch lah. But never mind. There you go, your circuit. Okay, this one, label it correctly because the question asks you to label it. So you are finding the resistance. So find out. Okay, use your V equals to IR. Then after that, okay, plot carefully on your graph. R against T means that your R should be on the y-axis. So this one, remember, is write down the axis label. Similarly down here, use your T. In this case, you are using degree C. So use degree C here as well. Plot your points, draw your best fit line. You'll be able to get a full mark. State and explain whether the resistance of the coil is related to, okay. What you will get is a straight line passing through 0, 0. Okay. Will you get a straight line? Oh, you won't get a straight line. You will get a straight line with a constant gradient, but you won't pass through 0, 0. So when you write down your statement, yes, it is linearly related, and the explanation is because the gradient is constant. Okay. Then after that, use your graph to estimate the value. So this one I leave it to you. Okay, last question. Yes. Just use V equals IL, you will find the V. Now notice that the current will only flow through your live wire, and then it will flow back to your power station through the neutral wire. So your live and neutral wire have the same current. Your earth current, because it says that it operates normally. So if it's operating normally, your earth wire will not have any current, because your metal casing don't have current. So how is a fuse act as a safety device? Refer to the book. Suggest a suitable fuse. So because it's 4 ampere, you need to select a fuse that is slightly higher. Okay. Explain why the switch is placed on the live wire. It is placed on the live wire because the live wire is at a high potential. So by placing the switch on the live wire, the circuit will be at 0 V if the switch is off. Okay, it's at 0 potential when the switch is off. However, if the switch is placed on the neutral wire, the circuit will still be at a high potential of 240 volt even when the switch is open, and this will make repair unsafe. Okay, because even if you go and put the switch on the neutral wire, if you off it and if you touch this coil, okay, this coil, okay, if the switch is going to be here, and if it's open, okay, imagine there's no switch here. So what happens is that the switch is open, but because now your circuit is connected to your live wire, the whole circuit will be at 240 volt. So if you are doing any repair and you accidentally touch it, the 240 volt is going to cause a potential difference, and then current will flow through you and it will kill you. Okay, so it is very important that your switch is on the live wire. Last part, so down here, use your P equals to VI. We have already calculated what is your V, what is your I. You find out this, convert into kilo W, kW. So every day you are going to switch on for 15 minutes. Okay, so you will get kWh here already, the unit. So multiply by the cost, you will find the cost per month. Remember to multiply by 30 days. That's it. The paper is actually quite straightforward, and you should be able to get A from this paper.